So it's good to see so many people here. Not just our group, but it's a band club. So today we're having Ray Garner present his PhD thesis. Find out what he's been doing these past many years. So for those of you who don't know me, I'm Chris Mihos. I'm Ray's thesis advisor. If you've not been in a thesis defense before, the way we do it here is that Ray will give a presentation of his research, which is sort of a colloquium level talk, hour long, 50 plus 10 minutes questions. And everyone is welcome to ask questions. Ray, I assume you're okay with people interrupting with questions, so
Yeah.
don't necessarily have to wait till the end. I will ask the committee after Ray's presentation. Then Ray will have another session with just the committee members, which will run typically 45 minutes, an hour or so. And so at that point, normally we do that in our conference room. Our conference room is currently stuffed with old computers that can't use it. So unfortunately, what we will have to do is after Ray's formal presentation, we will ask you all to vacate so that we can stay with him and talk. We've got the library here. We've got the lounge area. If you want to stick around, feel free to use those areas. And then for people who are sticking around afterwards, a little bit of an anticipation of a successful outcome, we will have a little bit of cake and celebration stuff. So anyway, with that, Ray has been working the past several years studying the galaxy M101 with data that was taken through our Burrell-Schmidt telescope in Arizona, through a series of narrowband filters, which gives you quite a bit of information both on the star-forming properties of the galaxy and on the stellar populations. And Ray has knitted all of this work together in a very interesting and coherent story about the evolution of M101. So Ray, let you take it over from there.
Cool. Thank you. Yes, so today I'm going to be talking to you about my PhD thesis, what I've been doing these last 5 years, locked away in these various offices, as investigating the galactic evolution of M101 with deep narrowband imaging. But before we get into the science, and there's a lot of science to cover, I want to give a quick shout out to this group of people. Especially my advisor, Chris. These people helped me a lot with the science, always gave me great feedback and helped me get it done. But of course, anyone not on this list, those of you here on Zoom, even those who couldn't make it today, thank you very much for supporting me throughout these last several years. I really would not have made it this far without you. So with that said, let's start with a big picture with how we think spiral galaxies form. So we think spiral galaxies form inside out. That is, as a cloud of gas collapses, the low angular momentum gas settles in first, forming stars on relatively short timescales, going through multiple generations. All the while, the outer disk of a spiral galaxy is still being formed from that collapsing gas. This results in many of the observational properties we see about spiral galaxies. They are exponential surface brightness profiles. They are brighter in the inner regions, dimmer towards the outer regions. They are metallicity gradients. They're more metal rich in the inner regions, metal poor in the outer regions. A color profile, they're more red, then become more blue, and that corresponds to an age gradient as well. They are older in the inner regions and younger in the outer regions. But although this is a great theory and explains many of the properties we see about spiral galaxies, it makes one problematic assumption, and that is that spiral galaxies evolve independently of each other, which we simply know is not true. Galaxies are constantly interacting and merging with each other throughout cosmic history. So a more interesting question is, how do those interactions and mergers change those basic observational properties? And one particular group that you can use to investigate that is the group I've picked, M101. The Pinwheel Galaxy, known Messier 101, although actually not discovered by Charles Messier, instead by his collaborator Pierre Méchain. So at least there's still an M there, just not the right one. And you can see it's a nice, beautiful spiral galaxy, these nice blue star-forming spiral arms. You can see these red ionized H2 regions where stars are currently being formed. But as you look at M101 and you compare it to other spiral galaxies, you notice that M101 is kind of weird. It has what I call its big wonky arm, this asymmetric spiral arm to the east. FYI, in astronomy images, north is always up, but east is to the left, opposite from what you'd expect. We've known about this asymmetric arm for decades, and we've always thought that an interaction, M101 got whacked by something many years ago to cause it to have this asymmetric arm. But when we look at its larger environment to look for the culprit, there's not much there. Unlike, you say, our local group, where we've got the Milky Way and Andromeda, two equally massive galaxies, maybe you include Triangulum in the mix, M101 is pretty much by itself in its group environment. It's the dominating member. It does have a few small, low-mass galaxies around it. So here are all the members of the M101 group. Of course, we have M101 at the center, just slightly under 7 megaparsecs away. It's slightly bigger than our own Milky Way galaxy. And then we have 3 satellite galaxies in this image. We have Holmberg 4. It's kind of a dwarf Magellanic type galaxy. This is the only time we're going to mention Holmberg 4, but it's there. However, there are 2 more important galaxies for this thesis. The one to the east of M101 is 5477. It's much smaller. You can almost count the number of stars in this image. But it is very close to M101 and positioned kind of close to that asymmetric arm. However, it's not that massive, certainly not compared to M101's most massive companion, 5474. Further to the south, but like I said, more massive, is kind of a dwarf spiral galaxy. You sort of see some faint spiral arms here. And it's peculiar in and of itself because unlike most spiral galaxies that have a bulge at the center, 5474 has a bulge offset to the north. It's kind of weird. We'll have to talk about that later. And then there's some background galaxies here as well, one of which will become important shortly. So M101 looks like it's got whacked, but there's not a big, massive companion near M101 to do the whacking. So as I said before, it's dominating its group environment. And we see evidences of this interaction throughout many different multi-wavelength observations. So aside from the asymmetric arm, here in this optical light, this optical image that Chris took 10 years ago, you can see that beyond the bright star-forming disk of M101, we have some low surface brightness light extended to the northeast and east, the northeast plume and the eastern spur. Hubble photometry of the northeast plume revealed that it has stellar populations consistent with being bursted about 300 to 400 million years ago. That's sort of the time scale for this interaction. When we look in the ultraviolet light, using, for instance, the GALEX telescope, we see that M101 has star-forming complexes beyond the radius where we think star formation should have stopped due to low densities. Specifically, we call this a type 1 extended UV disk. About 30% of all spiral galaxies have this kind of extended and XUV disk. And when we look at those other galaxies, those galaxies are often undergoing interactions. So this is further evidence that M101 has gone through an interaction. When we look at radiolight, looking at the neutral hydrogen gas, we see that it has an asymmetric plume, not in the direction of the northeast asymmetric arm, but towards the southwest. And higher resolution H1 data shows that there's actually a bridge of intermediate velocity gas between M101 and 5474. So all of these pieces of evidence have been used as support that around 300 to 400 million years ago, M101 was whacked by its largest companion, 5474. And indeed, a simulation published by Sean Linden and Chris just a year ago showed that many of the features of M101, like the asymmetric arm and the northeast plume, can be replicated with an interaction with 5474 around 200 million years ago. So As you see, as we go forward in time, M101 is going to get all kind of messed up. This is a relatively weak encounter. It is retrograde, meaning that right now we shouldn't see, huge, nice big tidal arms and ridges and tails. It's going to be relatively, M101's disk is going to be the main accident site here. So knowing that M101 went through this interaction, the big question I want to know is how impactful was this interaction? Did it leave debris throughout the M101 group? Did it mess up things about M101's stellar populations, its disk? And to answer that big, broad question, I have this wonderful data set with which to answer those. We have narrowband filters targeting 4 emission lines. The 2 brightest for hydrogen, H alpha and H beta, as well as some oxygen, O3 at 4959 and 5007, and O2 at 3727, 3729. It's amazing that we have all these filters, especially the oxygen filters. Hardly anyone has those. So we have great narrowband filters. But in addition to that, we have narrowband filters targeting the stellar continuum sitting adjacent to each of those emission lines. So we are able to, so as we do on-band minus off-band, we're able to get very deep, very accurate photometry. So as an example, here's our H alpha on-band. You can see all the nice, bright star-forming regions lit up in all of the galaxies. Meanwhile, in the off-band, there's still light here because the galaxy is still emitting light at these wavelengths. But you see all the star-forming regions are much dimmer comparatively. So when we do on minus off for all 4 of our filters, we get the continuum subtracted images, H alpha, H beta, O3, and O2. I should mention the images are much bigger than these cutouts. They're about 2.5 degrees on a side, covering around 6 square degrees of area. And you can see all the nice star-forming complexes in the entire group. You might even notice, especially in the H beta and a little bit in the O2, darkness in those images. I want to stress that that is not caused by bad over-subtraction, but instead we are actually measuring stellar absorption features in the disk of those galaxies. That'll be very important in the third part of this talk. So now that I've got this wonderful set of narrowband data, there are 3 questions that my thesis wants to answer. So are there any intragroup outlying star-forming regions near M101? How does the oxygen abundance vary throughout M101, and how do the stellar ages vary throughout M101? So first, let's talk about if there are any intragroup outlying star-forming regions near M101. But first, what are outlying H2 regions, star-forming regions? Well, these are star-forming regions that are well outside the normal star-forming disk of the nearest galaxy, often twice the isophotal radius away from the nearest galaxy. And they're sparsely distributed too. They're not all clumped together, otherwise we would have noticed them before. And sometimes they can lie in big, nice, neutral hydrogen gas clouds, or maybe even in the extended UV disk of the nearest galaxy. So there are essentially 2 options for where they can lie. Either they're really outlying, meaning they are new stars being formed in an area where very little star formation has happened before. There's very little underlying stellar continuum. An example of that would be, for example, these 2 objects discovered by Jessica Work in 2010, like here E2 and E3. You can see in the narrowband, they're emitting a lot of H alpha light, but in their broadband, there's not much old stellar population, if any, sitting underneath these star-forming regions. But they are associated with this cluster of galaxies. Their velocities are consistent with belonging to that group. So they are in the group. They're not, high redshift background objects. Alternatively, they could sit in an ultra-diffuse galaxy. This is an apt time to talk about these. There's just a big conference on UDGs recently. Ultra-diffuse galaxies are those that are large in size, galaxies that are large in size. They have an effective radius of greater than 1.5 kiloparsecs, but they're low surface brightness. You can see here in our V-band images, the 5 UDGs in the M101 group are sort of barely visible, DF1, 2, and 3, DWA, and DW9. These are potentially failed galaxies. Maybe they, as they fell into the group environment, they were stripped of their star-forming regions, or maybe they formed from strong galaxy outflows. We'll want to see if any outlying H2 regions actually lie in these UDGs or undiscovered UDGs. So now that we know what they are, what outlying H2 regions are, how do we look for them? Well, this is a big lesson for me in data quality, how to remove things you don't care about at the moment. So first, to start, we ran a segmentation map algorithm on our H-alpha on-band image, essentially looking for anything that was super bright in our H-alpha on-band. And that gave us over 35,000 different objects in our image. Now, not all of those are going to be objects we're interested in. For instance, we've masked, the big bright galaxies in the M101 group. There are also random little faint spots that we need to make sure are actual objects instead of noise. So we run through a bunch of different cuts. The signal to noise cut was the biggest, dropping it down to just over 3,500 sources. Then we removed bright stars in our own galaxy that are in the way, M stars, those cool stars that are in our own galaxy that have molecular absorption bands that play havoc with our filters, mimicking H-alpha emissions. Yes. Some people love them, we do not. We made a Balmer decrement cut. We cross-correlated with the Sloan Digital Sky Survey to remove high redshift background objects. And finally, we did a visual check. And that leaves us with just 27 sources in our catalog. And we split those 27 sources up depending on their emission properties. So if they are emitting in H-alpha, H-beta, and O3, we did not yet have O2 at the time, then they're in our 3-line sample, and there were 19 of those. And if they emit only in H-alpha and O3, but not H-beta, H-beta is oftentimes weak because of underlying stellar absorption, then there were 8 sources. And we are pretty sure we found almost everything that is to be found. We looked at extremely low flux limits, 10 to the minus 16 ergs per second per square centimeter, essentially the star forming the ionizing flux of a handful of O stars. We've looked down to extremely low limits. And when you look at where they are in our images, here you can see on the left of both sets, the H-alpha image, on the right, the B band, the broadband image. You see almost all of them, 25 of the 27, were near M101. And the H-alpha image, they do sort of look outlying. They're beyond twice the effective, twice the isotope radius of M101. That's the red circle. But when you look at our very deep broadband image, you can see they're really just extensions, the tips of spiral arms. So they're not really true outlying regions, H2 regions. They're just, part of the extended disk of M101. However, 2 of the sources were very interesting. Here on the top, the M101 group galaxy 5474, circled in orange, one object we found near it. And here on the bottom, the background galaxy 5486, about 40 megaparsecs away, circled in green, companion of it. So let's take a deeper look at both of those 2 interesting objects. For the one near 5474, for all of our objects, we compared them photometrically and structurally to other known catalogs. So 5474 was the faintest in the 3-line sample, the bluest in the entire sample, and had the highest H-alpha equivalent width in the entire sample. But if it was at the distance of 5474, it's very small. It has an effective radius of just about 30 parsecs, pretty consistent with the size of an H2 region. We were lucky enough to get spectroscopy of this image, thanks to help from Steve and Janesh at McDonald Observatory using the low-resolution spectrograph on the Hobby-Eberly telescope. So here you can see that spectrum, all the nice emission lines identified, and we were able to get a redshift, a heliocentric velocity of this object, about 266 kilometers per second, pretty consistent with 5474's velocity. So it really is an H2 region just sitting beyond the disk of 5474. For 5486, it's the exact opposite. It's the reddest in the entire sample, and it had the lowest H-alpha equivalent width in the entire sample. Additionally, you may have noticed in our broadband image that it shows not just a cluster of H-alpha emission, but some diffuse starlight to the west, sort of almost like a comet's tail. For a while, I was worried we caught a comet, but we did not. It has all of the properties consistent with a dwarf galaxy near 5486. And we also got its spectrum using the Hobby-Eberly telescope. You can see just the bright emission lines, a pretty steady stellar continuum, and getting its heliocentric velocity, it is consistent with being a dwarf galaxy nearby, a dwarf companion nearby to 5486. So we found an H2 region and a dwarf galaxy. But that begs the question, are there no outlying star-forming regions in the M101 group? We didn't find any in the diffuse gas clouds that Chris discovered in a 2012 paper. And we didn't find any in the ultra-diffuse galaxies that have been discovered, nor did we find any new ones. So that means that if star formation happened in either of these objects, particularly in the UDGs, then either it happened quickly and has already died out, or these are just really old objects. The already discovered ultra-diffuse galaxies have colors consistent with just being really old. In fact, here are those again. On the bottom now is our H alpha image. And I mean, yeah, there's just nothing there. They don't even have a diffuse emission. We were also able to constrain the faint end slope of the star forming luminosity function for the M101 group. And either it's got to have a very flat faint end slope, or it's got to be sharply truncated below 100th of a solar mass per year in order for us to star forming luminosity function. Yeah. What does this mean for the interaction? Well, it was relatively weak. When we look at examples of outlying star-forming regions of the literature, we find them in these big interacting systems, these compact groups like the 5291 group or even Stephan's quintet, where they're located in these tidal bridges and tails and at the in shock fronts. Meanwhile, I mean, M101, the M101 group is not one of these things. It is just M101 almost by itself. In fact, if you use the luminosity ratio between M101 and its most massive satellite, 5474, M101 is 17 times more massive than 5474. So it's going to be a relatively weak interaction. Additionally, M101 has probably not gone through very many mergers, if at all. It has a relatively anemic stellar halo. So that answers that question. There aren't really. We found essentially one object that could be interesting. So moving on to how does the oxygen abundance vary throughout M101? Now, people have been studying the abundances of M101 for well over 50 years at this point. It was one of the first galaxies targeted by Searle back in 1971. Here you can see a bunch of different authors using different techniques and calibrations and data qualities. And essentially, no matter who you ask, you all find the same answer. You have a metal-rich inner region and a metal-poor outer region, consistent with what is expected from inside-out growth of spiral galaxies. However, in recent years, newer methods have discovered that some galaxies have flattened abundances, a flattened abundance gradient beyond their isophotal radius, including actually our own galaxy. So for example, here is a bunch of spectroscopic data from the Khalifa survey, all piled on top of each other. And you can see you get this nice smooth exponential as predicted by inside-out galaxy formation. But then at about twice the effective radius, or at about the R25, it flattens out. Here's a few galaxies I can unpick from the literature, all showing there's a break radius at about 1 R25, and then it either flattens, or at least it's not as negative of a gradient if it doesn't completely flatten. And there's been numerous attempts at explaining why it's flattening out here. Either perhaps it's the barrier effect of co-rotation. Remember, co-rotation is where the pattern speed of the spiral arms matches the angular speed of the stars in their orbits around the galaxy. Maybe some other resonance caused by spiral wave dynamics. Maybe it's the addition of minor mergers or interactions. You can imagine as a galaxy interacts with the outskirts of another galaxy, it will cause a burst of star formation in a larger galaxy. Those stars, the high mass ones among them, will produce oxygen in their cores and then scatter their enriched guts across the outer disk of the galaxy, raising the oxygen abundance and causing it to appear flat. Or maybe there's just a different star formation efficiency in the outer disk. Maybe something weird is happening. So this is what we want to know about M101. Does M101 have a flattened abundance gradient in the outer disk? We have a lot of great data to try and answer that. Admittedly, we have to go through several rounds of corrections to get it up to par with spectroscopic data, which we are able to, but I do not have time to get into all of that. So we will just start talking about how we actually go about estimating abundances. So our narrowband filters were chosen specifically so that we can look at abundances using this particular strong line calibrator, the R23. It is simply the ratio of the O2 and the O3 lines divided by H beta. This is a well-known oxygen abundance calibrator, but it is also famously double valued. You can see here for any particular R23 value, you might have a metal-rich branch solution, a metal-poor branch solution, and a turnaround branch solution where those two converge. It is also dependent on a secondary parameter, either the ionization or the excitation state of the gas, basically a ratio of the O3 to O2 lines in some combination. We investigated the oxygen abundances using 3 different calibrations: Stacy's from 1991, Galactic and Cooley from 2004, and Piyugan and Thuan from 2005. There's a well-known literature on oxygen abundance calibrations. And I definitely don't have time to go into. I give you definitely a lot of references if you want to do some reading. But just know that that if you compare different oxygen abundance calibrations to each other, for example, if we pick a log of R23 of 0, Stacy's calibration says it has an abundance of 9.1. Galactic and Cooley says 9.3. Piyugan says 8.9. Those are all different quantitative numbers, and that is an unsolved problem in the literature why they give different numbers. But instead, you should compare them qualitatively. Abundances through these different calibrations, do they give the same general shape of an abundance gradient? Worry about that rather than say the exact y-intercept of those gradients. Like I said, I can give you many different references if you want to read about that. So before we estimate abundances, let's just compare our data, the R23s and the ionization parameter, the O32s, to spectroscopic data. So here's that. Log R23 versus radius, and log O32 an ionization state versus radius. Our data for M101 is in the blue points. We also estimated abundances for the 2 satellites shown in the orange and green points. And then the chemical abundances of spirals group, the CHAOS project, did spectroscopic measurements of 77 H2 regions in M101. So we can use their data as a comparison as well. So looking at the R23, especially for M101, we can see that we have the same broad parabolic trend here. We believe this parabolic trend is actually the double valued nature of R23 imprinted on M101's disk. So the inner region of M101 should be relatively metal rich. Then it should get more metal poor, the turnaround region, and then onto the metal poor branch in the very outer disk. You can also immediately see the 2 satellites all have pretty much the same R23 values. They're going to be pretty much the same abundance throughout their entire disks. When it comes to the ionization state, you can see CHAOS sort of comes up like this, whereas we get a bunch of lower ionization state regions at any given radius. We think this is because of CHAOS was limited to the auroral O3 4363 line, whereas we obviously don't have that limitation. Yes.
Do you have objects in common?
Yes.
And how do you find?
We did an extensive comparison. Aside from a slight offset, because they have 1 arcsec slit spectroscopy, whereas we have 3 arcsec aperture photometry, we're able to recover relatively well their data. So important for our discussion about M101 is where is the turnaround region? Where does it switch to the metal poor branch? We know the inner region has to be metal rich. There are no galaxies with a metal poor inner region. But where does it switch to be on the metal poor branch? It doesn't happen discretely here at say 1.3, 1.4. Rather, you can imagine it's really this band of it might still be on the turnaround region, maybe metal rich in the outer disk as well. So we'll have to do some analysis to see which abundance profile shape fits M101. Before I show that, I just want to show this lovely, amazing image. We were able to measure oxygen abundances throughout the entire M101 group, totaling 720 H2 regions, 650 of which were in M101. As a reminder, the most recent spectroscopic data only had 77 regions, so we're nearly an order of magnitude more than them. So not only can you see the spiral structure of M101, you can visually see the abundance gradient, where it's more metal rich in the interior and becomes more metal poor in the exterior. And you can see the two satellites are pretty much the same abundance throughout. However, when it comes to actually producing a radial abundance gradient, once again, we have to worry about what shape is it? Is it just that simple exponential as predicted by inside out galaxy formation, or is it broken? And so to help us determine that, we used a Bayesian method that, given a profile shape, what are the R23 values that will give you that shape? So let me break this down for you. So we've got log R23 versus radius. The black points in both plots is our actual data, is what we measure in our images. And the blue solid line follows the trend of the black points in the outer disk. You can see it's sort of decreasing in R23 in the outer disk. Meanwhile, the contours are probability density contours for what the R23 value should be given a pure exponential gradient or a broken exponential gradient. And you can see that if you look at the red line, which follows the trend of the contours in the outer disk. The pure exponential should be decreasing in the outer disk. Meanwhile, the broken exponential, we assumed flat in the outer disk, and you can see, yeah, the red line is flat. When we ran goodness of fit statistics, such as the AIC and the BIC on this, it actually told us that the pure exponential fits the best. However, by eye, it's not like the blue and red lines are lining up right on top of each other in either cases. So in reality, the gradient is probably somewhere in between these two extreme extremities. So calculating abundances, we'll go forward and produce gradients for both of these profile shapes. That is what we have here, the abundance gradient of M101. I'll break this plot down for you. We have oxygen abundance on the vertical and then radius on the horizontal, either in physical units or isophotal radii. The blue points are our H2 regions on the upper branch solution, the more metal-rich solutions. We kept the metal-rich solution in the inner disk. Like I said, there are no galaxies with metal poor in the inner regions, as well as turnaround branch solutions in the orange, yellowish circles. And then the outer disk, that's where we're left with one of two choices, where I've displayed the oxygen abundance for both the metal-rich and metal-poor solutions connected by these dotted lines. So there's not double the amount of H2 regions, there's the same H2 region, just two solutions. So in the outer disk, if we choose the metal-poor solution and construct a gradient with that, we get the dashed line, a pure exponential, with a slope consistent with spectroscopic studies of M101 and its abundance gradient.
Where do the spectroscopic studies go out to?
They go out to about where we go out to, except they use a different definition of what the R25 of M101 is than what we do. So they call it 1, we really say they go out to 2, and it's because of the asymmetry of M101. And we got it from Chris's 2013 paper. So yeah, spectroscopically, they go out here as well. If we pick the upper branch solutions in the outer disk, keeping them relatively metal rich, then we get a broken gradient that breaks at about 15 kiloparsecs or about an R25. Again, we ran goodness of fit statistics on this set of data, and those same statistics, the AIC and the BIC, told us that the broken exponential fits better. Remember, the Bayesian method told us that the simple exponential fits better. So this is more this is still pushing us towards that the true gradient is probably not as flat as this and not as negative as this, but somewhere in between. Now, how do we pick which one is the true gradient? Well, I like to go through sort of a pros and cons list of both possibilities, essentially answering what has happened to M101. If we believe the simple exponential, just given by spectroscopy, the gold standard, the poster child, then the pros are, yeah, it's what we expect. Galaxies just do that. That is a prediction and observation from inside-out galaxy formation theories. Also, when we look at galaxies in dense environments, in clusters, for instance, they only marginally have higher abundances, and they still have an exponential gradient. They don't change the shape of their gradient, and they're in dense, highly interacting clusters. So why would M101, an object in a relatively loose group, have enough change in its abundance profile? The cons for the exponential gradient is that M101 is strongly asymmetric. To construct these radial abundance gradients, you have to azimuthally average across the entire disk. And as Chris shown in his 2013 paper, the east and west sides of M101 have different surface brightness profiles, reaching a minimum at different radii. And we know that surface brightness profiles are linked to abundance gradient. Furthermore, I didn't have time to show in this presentation, we also detected azimuthal abundance differences between the east and west sides of M101. So averaging across the whole disk to produce a radial abundance gradient, which results in a simple exponential gradient, is ill-advised. When it comes to the broken abundance gradient, the pros are that you've seen this plot before. We see them in lots of different galaxies recently. Using, huh?
Isolated.
I believe some of them are in interacting systems, and
you said that dense environments had exponential.
Yes, in dense clusters. These are like, just two pairs of galaxies interacting with each other. So we see these in different galaxies, and they even use a different calibration than we are. So it's not dependent on us. Using a different calibration, you still get a broken abundance gradient. For M101, as I sort of hinted at before, the interaction with 5474 probably caused a burst of star formation in the outer disk, which would have imbued the outer disk with extra oxygen. Now the question is, how do you keep that extra oxygen in the outer disk and not have it mix interior? Well, for that, we could rely on co-rotation. Co-rotation has a sort of pumping out effect. It's sort of a barrier that gas cannot move across radially. So gas in the outer disk stays in the outer disk, gas in the inner disk stays in the inner disk. And this group, Scarano and Lepine in 2013, analyzed a bunch of different galaxies for their co-rotation radii, looking at rotation curves, and their abundance gradients, looking for broken gradients and where that break radius is. And they found almost a one-to-one relation. This blue point, in fact, is M101. M101's co-rotation radius is at about 15 kiloparsecs, where we find the break in our broken exponential. So that is a strong push towards believing the broken abundance gradient. However, there are cons. Co-rotation needs to be stable for long timescales for this to work really well. And if M101 just went through an interaction only 300 million years ago, then co-rotation might not be stable and might have shifted in that time. And so it might not be as strong as an argument. And it is worth mentioning that it is a well-known thing in the literature that using the R2-3 calibration, as we have, does often produce false breaks in their abundance gradients because it overestimates low excitation regions. Now, the person who suggested that was Pilyugin, and we used his calibration that he says fixes that issue, and we still found a break. We still were able to reproduce a broken exponential gradient, albeit the radius break was more interior than the other two calibrations. So, in my opinion, I believe the broken exponential, but there are pros and cons of both of them. So that answers that question. Maybe a broken exponential, maybe a simple exponential. Now, how do the stellar ages vary throughout M101? Well, returning again to inside-out theory, it predicts that there will be an age gradient radially, where the inner regions will be older, aka redder, the outer regions will be younger, aka bluer. And we have observationally found that trend. But spiral arms should complicate this trend. So, for example, here in this lovely animation of a spiral galaxy, there's a lovely web tool where you can like play with all the parameters of spiral arms. I suggest you should check that out. You can see, for instance, we got these lovely 2-arm spirals. You see these red H2 regions, and they're always on the outer edge of the spiral arm. This is illustrating what is known as the large-scale shock scenario. As gas enters into the arm, it gets compressed and forms stars. Those stars, the high mass ones among them, ionize the surrounding gas, producing H2 regions. Because those stars are high mass, they're going to not live very long, they're going to die out, leaving just low mass stars populating the interarm region and building up, the main stellar population of the galaxy. So this should actually produce an age or a color gradient, where there should be light-dominated younger ages near the spiral arms. And as you move into the interarm region, you should get older, redder populations. This is a prediction of the large-scale shock scenario of spiral wave theory. And numerous studies, numerous simulations support this idea, especially in galaxies with bars or a single pattern speed, the golden poster child of spiral density wave theory. However, observationally, finding these has been very hard to do. Many people use broadband colors to try and find these, which of course, whenever you use broadband colors, you have to be wary of the age metallicity degeneracy. Is that population red because it's old, or is it red because it's metal rich? Similarly for blue metal poor populations. Some people have had success. Martinez Garcia, in a sample of 13, found 10 galaxies that evidence this large-scale shock scenario gradient. However, they use the Q parameter, which is a combination of optical and near-infrared photometry. And then this group, Sanchez-Gill, in their sample of 6, found 2 galaxies using a combination of optical and far UV photometry. So you've got to use almost multi-wavelength photometry to get rid of the to control for the age metallicity degeneracy. Now, obviously, you don't want to use photometry. You want to use spectroscopy, where you can resolve those age indicators, those age spectral lines. However, spectroscopy still suffers from an inability to look at the low surface brightness outskirts of galaxies, and especially the big galaxies that are close up to us so we can get fine spatial resolution. They're so big on the sky that using integral field spectroscopy to cover it is really resource intensive and only available to us in very recent years. So, right in between, as you might have guessed, is narrowband photometry. Here again is our H-beta and our O2 images, this time scaled so you can see the absorption features, the dark features in M101. We're going to focus on M101 here. In the H-beta band, you might imagine we're measuring the H-beta absorption line. But what the hell are we measuring in O2? There is no O2 absorption line. So to investigate that, I use the SAD modeling code SIGAL to produce single burst populations, the SAD, the spectrum of a single burst population. So here you can see on the left, the wavelength region for our O2 filters, on the right, the wavelength region for the H-beta filters. The on band is the darker of the two rectangles, and the age increases going bottom up. So a mega year old all the way up to 13 gigayears. In the H-beta, you can see, we're only measuring the H-beta line. And here we recover the trend with the Balmer lines, where it starts off relatively young, as O and B stars have very weak Balmer absorption lines. Then as those stars die out at around 400, 500, 600 megayears, leaving just A stars, which have the strongest Balmer lines, you can see the absorption line gets deeper. But then as those stars die out, that Balmer line weakens. In the O2 bands, we of course see all these higher order Balmer lines that show the same trend, starting off weak, getting stronger, and then weakening again. But you also see there's a change in the slope of the continuum as those O stars die out and as metallic bands, molecular bands, start to come in at old ages. In fact, I think our O2 off band sits on a cyanogen band. So in combination, we should be able to get some constraints on ages by measuring equivalent widths through both of these filters, these filter sets. Going forward, we're going to continue to call this H beta. Because there's no O2 absorption line, we're going to call this 3746 to remove any confusions. So how do these equivalent widths change as a function of age? Well, we did a lot of exploration with Seagal with many different assumptions. These have exponential star formation histories, Chabray IMF, solar metallicity. There's a dusk model in here. We explored all of these different parameters. Here I'm only showing you 2 of them. So first of all, on these plots is the equivalent width in 3746 in the O2 filters on the vertical, and equivalent width in the H beta filters on the horizontal. On the left shows what happens to these stellar populations as you change the E folding time scale of the star formation history, what they call tau. So for example, a tau of 500 megayears, you can imagine is sort of like an elliptical galaxy, a burst early on and then just kind of fades away. Meanwhile, a tau of 30 gigayears is almost a constant star formation rate. You can think of as a late type spiral galaxy, just always sort of chugging along and making stars. You see dots here, these are ages of these populations, so 50 megayears, 600 megayears, 10 gigayears, as those populations get older. So they all start off on the same line, and they all decrease as those Balmer line absorption lines get deeper, until they reach the time scale where A stars start to die out. In which case, H beta decreases relatively rapidly. Meanwhile, the O2 filters are still measuring spectral features beyond that time, where the Balmer lines have died out, but we're starting to measure metallic lines, which is why this is going in quote unquote emission at late time scales. It's not like there's actually emission lines here, but because of those, especially that cyanogen band in our off band, it just means that there's more flux in the off band than the on band. And so the biggest thing you notice is that we've essentially got these 2 prongs. I used to call these paperclip plots because it looked like as you unfold a paperclip, you can almost lay one on top. But you have these 2 prongs. It turns out that in addition to a main stellar population, if you add in a recent burst of some age, it actually folds the old prong, back towards the younger prong, deepening those Balmer absorption lines again. So these are the 2 big parameters that we are sensitive to. We are not as sensitive to metallicity as some other studies because the Balmer lines don't have a strong change with metallicity. And of course, we have previous metallicity studies to help us constrain. And we're not as sensitive to dust because our narrowband filters are placed essentially next to each other in wavelength space. We don't have to have a strong dust correction. And we also have other studies that tell us roughly what the dust content in M101 is. So using these models, we want to see how the different environments in M101 fall onto these plots. So first we got to define some environments. So we define a central region. This is basically visually defined where it's hard to distinguish spiral arms. It's much bigger than what other people would call a center, but it's based on how we're defining. So less than 120 arc seconds or 4 kiloparsecs. We define some spiral arms and inter-arm regions using logarithmic spirals. Using the B-band image, essentially, I decided where the arms are, threw them back into Python, fit lines to them in natural log versus angle space, and we get these beautiful spiral arms out. The inter-arm regions are between the arms. We use the H-alpha image to determine how wide the spiral arm masks are to encompass most of the flux in those along the arms. They're around 2 to 2.5 kiloparsecs across. And then we have to make a sort of a signal to noise cut. The inner disk of M101 is just much brighter. It has better signal And so we make a signal to noise cut, splitting it at about 430 arc seconds, or 3 times the disk scale length. You can see that here. The black circle here is between inner and outer disk. And so the inner disk will investigate using medianed 9 by 9 pixels. The outer disk will be in medianed 40 by 40 pixels for particular good quality regions of the outer disk. So let's look at the inner disk first. Plotting all of the points on that diagnostic plot, the W3746 versus WH beta plot. And I've also thrown in some of the model plots. Here they're colored by radius from the center of M101. And we get essentially the radial age gradient back. You see that there are dark points, more inner points here along the older ages of the track. And as you go further out, it moves towards the younger age as well. And I have investigated. There's not a huge population of yellow points sitting underneath the old stuff. And you also notice that not everything is sitting along the 2 prongs. There's stuff in between. Remember, that's just any recent burst of star formation, whether that's from the interaction or just normal stochastic spiral galaxy star forming properties. When we split it up into those morphological regions, here we can see the central region in red, much older, slightly older than the star forming spiral arms. But the interarm region, the green contours, are interesting because there's part of them are sort of like the spiral arms. Part of them are more like the center of the galaxy. So we can select 2 different regions, essentially where those dark contours are, and see where are these in the galaxy. The spiral arm points, the like arm interarm regions, and the true arm interarm regions. And when we do that, we get this lovely plot. So here you can see the spiral arms of M101, the masks that we use, as well as all of the points along the spiral arm. Any emptiness along the spiral arm is caused because we masked the H2 regions in M101. So where there's emptiness, there's probably an H2 region that we're not looking at. You see that the like arm interarm regions, the things that have the same spectral properties as spiral arm, all sort of lie along one edge of the spiral arm. Meanwhile, the true arm, the older stuff, lies along the opposite edge. We think that we are seeing the age gradient of the large-scale shock scenario, where the green, the older stuff, has yet to move through the arm, being imbued with new stars, producing a younger-looking population by light. And we think we're able to do this because we're not using broadband data. We're using pretty accurate narrowband data, measuring a bunch of different spectral features, and it's relatively insensitive to dust. So we think we are seeing a quasi-steady, a relatively ordered inner disk of M101. The outer disk of M101 tells a different story. In the outer disk, here's our H beta on image. We're going to select a handful of regions in the outer disk. We try to remain azimuthally unbiased. You see, for example, 1A through 1E are on the northeastern spiral arm towards the northeast plume. We've got things in like a deep interarm region along the south, a few to the west. And here, you can see where they lie on the diagnostic plot. The contours again are for the inner disk, just to compare. And you can immediately see that they're all shifted towards stronger absorption, aka towards younger ages. Plotting some different star formation history tracks on here, you see that many of them are consistent with a fading or a near constant star formation history, where there's a relatively burstier type of population. They're all relatively young. There's not very many old populations. For example, regions 1A through 1E, the blue colored regions here, are all relatively young, all have are consistent with star formation histories similar to what Chris found using Hubble photometry of a near constant or fading star formation history. However, there are those 3 outliers over there, regions 3, 5, and 12. Region 3 is in a deep interarm region, and we don't expect it to be very young. We expect it to be mostly old underlying stellar populations. And yeah, that's exactly where it sits on the older track there. Meanwhile, 5 and 12 those are both located on the western side of M101. This is a side that did not participate strongly in the 5474 interaction. So we don't expect it to be filled with young stars. Instead, it's probably just, general stochastic star formation. So looking at the outer disk, trying to explain that, radial migration is probably happening. It's happening all the time, but it's not as significant. It's not moving young stars out into the outer disk. Rather, they're probably still very scattered, full of young stars from the interaction. Here is a simulation from Dobbs and Pringle. This is supposed to mimic the M51 interaction, but I've always found if you tilt your head and look this way, that's M101. I mean, this is the asymmetric arm. And you can see that their ages in the simulation, they're all over the place. Some of them are the same age along large swaths of a spiral arm. Some of them change radically along a spiral arm. They're very highly scattered. So the outer disk is simply younger, more scattered than the inner quasi-steady disk. But how do we join those two? Well, I propose that M101 has dynamic spiral arms. These are not long-lived spiral arms of a single pattern speed, but instead arms that join and disconnect over short time scales, giving the appearance of a long-lived spiral pattern. A consequence of dynamic arms is that there is no single pattern speed for that galaxy. Here, Mate in 2009 actually measured 3 different pattern speeds for M101, varying radially, getting lower as you go out. And this is in simulations of these varying pattern speeds. You also actually get the stimulation of single-armed spirals, just like what we see in M101. This is through something called mode coupling, where the resonances of 2 different pattern speeds overlap. So perhaps the co-rotation radius of an inner pattern speed overlaps with the inner Lindblad resonance of a further out pattern speed. So perhaps M101 is quite dynamic. So let me summarize what we talked about in the last hour. So we have found that there are really no outlying H2 regions in the M101 group, down to extremely low flux limits. We've looked at a lot of abundances for a lot of H2 regions in the M101 group and found that M101's gradient is either a simple exponential or a broken abundance gradient. I personally believe the broken fits better, but there is caution. There are pros and cons of both. Hopefully I've shown well that the inner disk is pretty quasi-steady. It has that radial age gradient and also has some changing ages across the spiral arms. Meanwhile, the outer disk is pretty young, caused by that tidal interaction, and they're joined by a dynamic spiral arm pattern that both builds up the spiral pattern at large radii and allows for a single arm spiral to emerge. Before I end, I do just want to bring up some future ideas where I'd like to go in the future. So I focused on M101 throughout this last hour, but I do want to turn my attention to 5474. It is interesting in and of itself. It got a little bit of a look a few years ago where a group of authors proposed that maybe this isn't a bulge sitting in the plane of the galaxy, sitting in the disk, but instead a companion elliptical galaxy we're seeing along the line of sight. It just happens to be in the way. They did a simulation and that their simulation fit. To break that observationally, some high resolution spectroscopy could help break that difference by looking at radial velocity differences between the absorption lines in the bulge and the emission lines in the disk. That is an idea there. Although I spent a lot of time talking about the chemical abundance of M101, despite all of the abundances that we were able to measure, there are still clearly some uncertainties using the method we use as well as the data. And so that can really be overcome with integral field spectroscopy surveys of M101, 2 of which I currently have access to, are the Hobby Eberly Telescope Dark Energy Exploration Survey, HETDEX, where they're looking to help constrain information about dark energy, but in doing so, they got IFS spectra of the entire disk of M101, sadly only covering from 3,500 to 5,500 angstroms. They're missing the H-alpha, nitrogen, and sulfur lines, so it limits its usefulness, but it's still a great data set that I hope to play around with. And then for those of you who don't know, I have a postdoc lined up at Texas A&M working on the Signals project, where they have gotten Fabry-Perot spectroscopy for 60-something galaxies, including M101, although missing that weird chunk there. And they've got some great data. I'm very excited to start playing around with that. And then I would like to continue to apply the lessons I've learned here in the M101 group to other galaxies. So for example, we know abundances of galaxies connect to other properties of them, like for example, the mass-metallicity relationship. But how do the abundance gradients connect to other properties? So for example, if there is a break in an abundance gradient, how does that connect to a surface brightness profile? Is there a break in that surface brightness profile of the same radius? And then what controls the azimuthal abundance variations? We found some in M101, but there's debate in the literature over whether you need a strongly barred galaxy or a non-barred galaxy. Here you see a lovely barred galaxy with azimuthal abundance variations across 0.3 dex, but that's another thing that I'd like to look at. So with that, I will end, and I'd be happy to take questions.